This video is looking at finding stationary points and determining what the stationary points are, and also how to find points of inflection. It's very important that you pause the video at this point and you copy down all the notes on this page and learn them, and also copy or screenshot and print out the diagram on the right hand side. Now, we're going to look at the method for finding the coordinates of the turning points and determine their nature. So the first thing we're going to do here is we're going to do a quick summary or review, if you like, of what the formulas are. So what we have here is we've got to have a local maximum, and the formula for a local maximum, there are two. The first formula is dy dx has to be equal to 0, and d2y by dx squared has to be negative, has to be less than 0. Now let's quickly remind ourselves why that is the case. So if we're looking at a maximum, the second derivative is looking at how the slope changes. So if we look at the slope coming into a maximum, it's positive, then it goes to 0, and then it becomes a negative slope. So consequently, the rate of change of the slope is negative. It's moving from positive to a negative. So for a local maximum, d2y by dx squared is negative. Now we're looking at local minimum. And for local minimum, dy dx is equal to 0. d2y by dx squared is greater than 0. And a quick reminder why. But there's a picture of a local minimum. As we're coming in to the local minimum, the slope is negative. When we get to the local minimum, the slope is 0. And when we come out the other side from the local minimum, we've got a positive slope. So what's the overall change in the slope? When we are at a minimum, the overall change is from negative to positive, so it's a positive change in the slope. Hence d2y by dx squared is greater than 0. Quick reminder, don't confuse turning points with stationary points. A turning point is purely a maximum or a minimum. Okay then, let's do the method. No matter how the question is phrased, this is always the method. The first thing we do is we write down what y is equal to. And y is equal to, straight from the question, x cubed minus 9x squared plus 15x. And now we're going to be doing dy by dx is equal to 3x squared minus 18x plus 15. And then we're going to do the second derivative, d2y by dx squared is now equal to 6x minus 18. Okay, the language we use and the way we write it down should always be the same. So now I'm going to be writing down 4 local maximum stroke local min. We have a formula. For local maximums and local minimums, we have a formula, and the formula is quite simply dy dx is equal to 0. We now go up here and we know that dy dx is 3x squared minus 18x plus 15. So we can now write down, therefore, 3x squared minus 18x plus 15 is equal to 0. Don't forget, you are allowed to divide an equation across by a constant, by a number, but you're not allowed to divide across on an equation by an x. So here we notice that 3 goes into 3, 18 and 15, so we can actually divide everything by 3. So dividing everything by 3, we end up with 1x squared minus 6x, and 3's go into 15 5 times. The reason why we do that, of course, is because it makes solving the quadratic equation maybe that bit easier. 1 times 5 is going to give us 5. So we're looking for a factor pair that will multiply to give 5, but add up to give minus 6. So the one that works is going to be minus 5 on minus 5. So there we have it. It would add up to give the minus 6. So then we can break this quadratic down into x squared minus 1x minus 5x plus 5 is equal to 0. Now we're going to factorize in pairs. We're going to factorize in pairs. Common factor here is x for the first pair, leaving us with x minus 1, which allows us to write x minus 1 in here. And now I'm going to choose to take out a minus. I will check that in a few minutes. The common factor for 5x and 5 is 5. Is the minus sign correct? We're just about to find out. Minus 5 on x is minus 5x, so that minus sign was correct. Okay, so now what we can do is we can go to the next line. So we've now got x minus 1 on x minus 5 is equal to 0. And then from that, using the method of zeros, we're going to have x minus 1 is equal to 0, or x minus 5 is equal to 0. Consequently, we're going to have x equals 1, and we're going to have x is equal to 5. Now, the only issue at the moment is, although from a sketch we could probably work out which one was the maximum and which one is the minimum, we're going to use calculus methods to work it out today. We now need to determine which one of these is the maximum and which one of these is the minimum. So we're now going to come back over here and we're going to write down the next part, which is the test. And the test is using d2y by dx squared. So we're testing using d2y by dx squared. And the test is on, well, d2y by dx squared is 6x minus 8. So we're testing using d2y by dx squared, and we already know from over here that it's equal to 6x minus 8. What are we testing? Well, we're testing the two values of x, which we have just calculated. So the first value of x we're testing is we're going to test x equals 1. So using the empty bracket method, d2y by dx squared is equal to 6 empty bracket 1 minus 8. And when we work that out, we get minus 2. And then here we're going to test it on x equals 5. So once again, we copy down the empty brackets. d2y by dx squared is equal to 6 on, well, x is now equal to 5 minus 8. And 6 on 5 is 30. 30 30 take 8 is going to be, 8. It's going to be 18. Apologies. 6 minus 18 is going to be minus 12. And here it is also 18. So 30 take 18 is going to be plus 12. Now minus 18 is less than 0. And because it is less than 0, we now know that because d2y by dx squared is less than 0, we actually now have that this is a local max. So we now know that this is the local max. So we know that x equals 1 is a local max. And the next one, we've got d2y by dx squared is equal to 12, and 12 is greater than 0. And because 12 is greater than 0, that means d2y by dx squared is greater than 0. So consequently, it's greater than 0. And therefore is a local minimum. So we've now got here that we have a local minimum. And x equals 5 is a local minimum. Now the question did say quite clearly that we had to find the coordinates of the turning points, which means if we're finding the coordinates of the turning points, we need to find the corresponding y values in order to finish off this problem. At the moment, we have determined the nature, but we haven't got the y values. So this is part 3 of the problem, where we write down that y is equal to x cubed minus 9x squared plus 15x. We're then going to be finding out what the value for y is when x equals 1, and we're going to find out what the value for y is when x is also equal to 5. So using the empty bracket method, we've got empty bracket to be cubed minus 9 empty bracket to be squared plus 15 on an empty bracket, and we're going to be working out the output number in a minute. And since we've got 2 input numbers, we need 2 sets of these empty brackets. Okay, we've now done that. In the first one, we're putting 1, 1, 1, and then we're going to be putting 5, 5, 5. Now, you could pause the video at this point and you could reach for your calculator and you need to work this out. When you work out the first one, you get a value of 7. And when you put 5 as an input number, you get a value of minus 25. So the input number was 1 and the output number was 7. And for this one, the input number was 5 and the output number is minus 25. And x equals 1, we have to go back up and check, is a local maximum. So this point is a local maximum. And this point here is a local minimum. And that's the end of the problem. Now, that is the end of the problem. but sometimes you are required to sketch it. So we're going to now, even though this is not part of this problem, we are going to sketch this cubic equation. Now going back to the fourth year, it is a positive cubic equation. So on the right hand side, we know it finishes up going uphill if it's a positive cubic equation. A cubic equation has two turning points, so I'm just doing a sketch here. Going backwards, it's not particularly very neat. This could be a rough sketch to begin with. So once I've done the rough sketch, it's much easier if I draw it going left to right. I can then do a neater. There we go. So the local maximum is at the point 1, 7. So there's your point 1, 7. There's your local maximum. Here's the local minimum. And this is the point 5, minus 25. It depends on the range of values, but a local maximum and a local minimum doesn't necessarily imply the highest or lowest. As you can see on the right hand side, the graph is going up. So the maximum value of the graph could be infinity. And on the left hand side, my graph at the moment is drawn to finish here, which means my local minimum point is actually the minimum at the moment. But if I was to extend my graph to continue it going down now, and this is where the graph ended, then this would be the minimum point, and over here would be the local minimum. So basically where you have a mountain top or valley bottom is a local maximum and a local minimum. Okay, moving on to the next example. This one is actually purely focusing on finding a point of inflection. So what's the formula for a point of inflection? Well, the formula on our course for a point of inflection is d2y by dx squared is equal to 0. But at university, there's an additional formula. And point of inflection at university is d2y by dx squared is equal to 0, but d3y by dx cubed is not equal to 0. Now, this one here is no longer on our maths course, but in a year's time, it could be quite useful. So I'm drawing it to your attention. We might even use it today. And as you might have guessed, d3y by dx cubed is the third derivative. But for the Leaving Cert examination, you don't have to go that far. Okay then, so here we've got y is equal to x cubed minus 3x squared minus 2. And we're going to differentiate it once, so dy dx is equal to 3x squared minus 6x. We're going to differentiate it a second time, d2y by dx squared is now going to be equal to 6x minus 6. You may notice there is 3 goes into 3 and 6, but this isn't equal to 0 at the moment. You can't divide at this moment in time across by 3, and you can't divide by 6. It's the most common error. It's really quite annoying when it happens because people just end up getting minimal marks then. It's quite disappointing. Now, for a point of inflection, because this is what this question is about, getting back to the question, we were told to find the point of inflection. Well, we know that the point of inflection formula for our course is that one there. So write this down, always write it down. For a point of inflection, Inflection, you might come across it in future studies. There is another way of pronouncing it, and inflection can also be written as inflection, just in case you come across that word and wonder what it means. Inflection is the same as inflection, so just be aware of that for future. Now, for a point of inflection, we know that d2y by dx squared is equal to 0. Consequently, we know therefore that 6x minus 6 is equal to 0. This is a linear equation, so bring the minus 6 over. Then we divide both sides by 6, and we are then going to be cancelling out the 6's there, and then we're going to end up with x is equal to 1. What we're going to do now is we are then going to substitute this back in, because it did say find the point of inflection, which means we want the y value. So if we want the y value, we have to quote the y equation. So y is equal to x cubed minus 3x squared minus 2. And we're looking at an input value of 1. So again, we're using the empty bracket method. So empty bracket method, we've got empty brackets cubed minus 3 on empty bracket squared minus 2. The input value is going to be 1. And now we're going to put this into the calculator and get the answer. So when we put 1 into the calculator and get the answer, we should come out with a minus 4. Do double check on that. So the input number was 1 and the output number was minus 4. So therefore, there is our point of inflection. So our point of inflection is equal to 1 comma minus 4. Now, this next bit is not part of the course, but I'm going to do it anyway just for university. We know that d2y by dx squared is equal to 6x minus 6. When I differentiate for the third time, d3y by dx cubed, I get x. So for point of inflection, this third derivative is not allowed to be equal to 0. So when I substitute x equals 1 in, I get d cubed y by dx, d3y by dx cubed is equal to empty bracket. It's going to be 1, which of course is equal to 1, which of course is not equal to 0. So it satisfies that university rule. So therefore, this definitely is a point of inflection. Okay, moving on to the next example. Please note that on each example on the top right-hand corner, you have been told what questions to do. I'm providing you with a worksheet for this activity, and this worksheet is at the end of the video. So you can freeze frame at the end of the video on the exercises and do a screenshot, and you can work off those. Okay, we've got to verify that the curve y equals x plus 2 divided by 2x minus 3 has no turning points or points of inflection. So what do we know about turning points? Well, for turning points, dy dx is equal to 0. That's the formula for turning points. It doesn't ask us about the nature of the turning points. And because it doesn't ask us about the nature of the turning points, we don't have to write down, local max, local min, d2y, etc. It's just turning points. The formula for turning points is dy dx is equal to 0. the formula for a point of inflection. So for a point of inflection, we have d2y by dx squared has to be equal to 0. So for no turning points, then dy dx is not equal to 0. And for no point of inflection, we have to show that d2y by dx squared is not equal to 0. So we're doing the opposite. Let's get about our business. So at the moment, we've got y is equal to x plus 2 over 2x minus 3. And we need to do dy dx. And to do dy dx, it's a quotient rule. So we've got bottom times differential of top minus the top times the differential of the bottom all over the bottom to be squared. So what's the bottom equal to? The bottom is equal to 2x minus 3, and the differential of the bottom is quite simply equal to 2. The top is equal to x plus 2, and the differential of the top is quite simply equal to 1. So we're going to be doing the differential, we're going to do the bottom times the differential of the top, and then we're going to be doing the top times the differential of the bottom all over the bottom to be squared. So let's sub everything in now. So we have dy dx is equal to, well, the bottom is going to be 2x minus 3 times the differential of the top, which is going to be equal to 1, minus the top, which is x plus 2, times the differential of the bottom, which is going to be 2. And that's going to be all divided by the bottom to be squared, which is going to be 2x minus 3, all to be squared. Now we're going to be doing dy dx. I'm going to do a tidy up line. I'm going to bring the 1 to the front. This is my advice that you always do, because there's lots of mistakes here when people don't tidy up. I'm going to bring the 2 to the front of this bracket. So all I'm doing is a tidy up line. I'm not doing anything else. And then over the bottom to be squared. Okay, so now we need to work it out. So dy dx is now going to be equal to 2x minus 3 minus 2x minus 4 all over the bottom which is 2x minus 3 all squared. You should spot at this stage that we've got a plus 2x and a minus 2x, which therefore cancel. So dy dx now becomes minus 7 over 2x minus 3 all to be squared. Now, before I answer the question, I already know, because it mentions point of inflection, that I have to differentiate this a second time. So I'm going to do all the working out for the first derivative and the second derivative first before I finish off the question. So I'm going to come up into here, into the empty space, and I'm going to write out what I've got so far. I've got dy dx is equal to minus 7 divided by 2x minus 3, all to be squared. Now I could use the quotient rule on this, but it is, trust me on this one, it is actually easier in this case to use the chain rule. And if I'm going to use the chain rule, then what I'm going to do is I have to bring the bottom expression to the top. And when I bring the bottom expression to the top, then the power of 2 becomes a power of minus 2. When you're using the chain rule in this format, you have to remember that the priority function is the minus 2, and the secondary function is the 2x minus 3. And that we differentiate the priority function first, and nothing else changes. So let's see this in action. So we've got d2y by dx squared is, well, focusing on a, which is multiply by the power. When we multiply by minus 2 on minus 7 becomes a plus 14. Nothing else changes. We multiply by the power and then we put the power down 1. And don't forget, nothing else changes. And then what we do is we multiply by the differential of what's inside. And the differential of what's inside is we multiply by 2. And now we're going to do the tidy up line. And the tidy up line is that we've now got d2y by dx squared. Well, we multiply by 2 on the 14 and we get 28. But you should notice that this is a negative power. And because that's a negative power, it means that we can bring this to the bottom of the fraction and write it as a positive power. So therefore we've now got 2x minus 3 to the power of 3. Now, let's go back to the formulas we have written above in red and brown. We've got, for turning points, dy by dx is equal to 0. So, but the question wasn't about turning points, it was about no turning points. And because no turning points means that this formula becomes dy by dx is not equal to 0. And it says for a point of inflection, and we're not doing for a point of inflection, we're doing for no points of inflection. So it's no points of inflection, which means d2y by dx squared is not equal to 0. So what I'm going to do now is I'm going to quite simply write here, finishing off. We know what the two formulas are, so now we're going to use it. Well, dy by dx is quite simply never equal to 0 for all values of x. Now, the reason why you may want to write this down is the only part of a fraction that makes the fraction 0 is the top. And basically, the reason why I know that this dy dx can never equal to 0 is because the top is equal to minus 7, and clearly minus 7 is not equal to 0. So this is not equal to 0 for all values of x, because the top is equal to minus 7, which is not equal to 0. And over here, same argument. This is not equal to 0, and the reason why it's not equal to 0 is because the top is equal to 28, and the top is not equal to 0. Simple as. And that's all you have to do in order to prove this question correct. Okay, moving on to the next example. Well, the next example looks a bit longer, but in actual fact, we're going to be treating it in exactly the same way. It says here, you've got y is equal to x to the power 4 minus 4x cubed. Find the coordinates of the stationary points for this particular problem. And then determine their nature, find the x and find the y intercept. It's a long question, but the way we approach this, I'm going to be totally honest with you, is exactly the way we just approached the last few examples. So, and the bottom line is, don't change the approach. It works. It works. So here we go. So we've now got here, we've got y is equal to x to the power 4 minus 4x cubed. We're looking at stationary points and we're looking at determining their nature. So this time it's making reference to stationary points. Now there are 3 stationary points. There's only two turning points, a local max, a local min, but there are 3 stationary points. So the first stationary point is a local max, and the formula for local max is dy dx is equal to 0, but d2y by dx squared is in actual fact less than 0. And then we have a local minimum. And for a local minimum, the formula is dy dx is equal to 0, but d2y by dx squared is greater than 0. And then we've got one more stationary point. And the very, very last stationary point is a horizontal point of inflection. So we've got a horizontal point of inflection. And for a horizontal point of inflection, we have dy dx is equal to 0. This is for a horizontal point of inflection. And d2y by dx squared is also equal to 0. For our course. Now please note, generally speaking, the formula for point of inflection is purely that. But generally speaking, a point of inflection is not a stationary point. A horizontal point of inflection is. So whichever way, we need to actually differentiate this twice. So we've got dy by dx is equal to 4x cubed minus 12x squared. So we've also got here d2y by dx squared is equal to 12x squared minus 24x. Okay. As before, always write this down, local max stroke local minimum, we have a formula. And for both local max and local minimum, we know that dy dx is equal to 0. Therefore, we now know that 4 x cubed minus 12x squared is equal to 0. Of course, dy divided by dx equals 0 is also true for a horizontal point of inflection, but we don't usually write that down. What's the common factor? Well, can we divide across by 4? Don't forget, never ever divide across by letters. If you do, you will lose a solution and you will lose a heap of marks. But you can divide across by numbers. So we've got x cubed minus 3x squared is equal to 0. Do we have a common factor? We surely do. The common factor for this pair of terms is x squared. So we've got x squared, open bracket, x minus 3 is equal to 0. Using the method of zeros, we've got x squared is equal to 0, or we've got x minus 3 is equal to 0. X squared equals to 0 yields the solution x equals 0. X minus 3 equals 0 yields the solution x equals 3. What we're going to do now is we're going to determine the nature. If we're determining the nature, we're going to be using the test function, and the test function is going to be the d2y by dx squared. And the d2y by dx squared is 12x squared minus 24x. Again, you can't divide across by 12. You can only divide across by 12 when you've got numbers on both sides. So you haven't got a number on the left-hand side, you've got an algebraic expression, which is d2y by dx squared. So now, the first test value is x equals 0. So we're going to test for x equals 0. Bear with me when I just divide off the page slightly. So x equals 0. So when we test using x equals 0, d2y by dx squared is equal to 12 on 0 to be squared minus 24 on 0. And when we work that out, the answer is 0. And we can see from our formulas above that this is going to be a point of inflection. So x equals 0 is a point of inflection. So we've now got the other test value is testing using x is equal to 3. So we've now got d2y by dx squared is equal to 12 on 3 to be squared minus 24 on 3. Okay, I'm going to need to reach for the calculator on this one. So 12 on 3 to be squared minus 24 bracket 3 close bracket is equal to 36. And 36 is greater than 0. So because 36 is greater than 0, then we've got d2y by dx squared is greater than 0. So we're going to be looking at d2y by dx squared is greater than 0, and which means it's going to be a local minimum. It's going to be a local minimum. Now we're going to be doing a sketch of the curve, and when you do a sketch of the curve, you need to know key values. So we need to work out the y values for these two input numbers. So back over onto the left-hand side, I'm now going to write down y is equal to x to the power of 4 minus 4x cubed, and I need to work out the corresponding y values for x equals 0 and x is equal to 3. So using the empty bracket, so it's empty bracket to the power of 4 minus 4 on empty bracket to the power of 3. There's a naught going in here, so therefore the output number is naught. So the input number is naught and the output number is naught. Here we've got y equals empty bracket to the power of 4 minus 4 on empty bracket to the power of 3 is equal to, the input number is 3, the input number is 3. So when the input number was 3, then once again we need to reach for the calculator or do it in our heads, and we're going to get 27. So the input number was 3 and the output number was 27. So what we now have is we know for the first one, if you remember, the x equals 0 gave d2y by dx squared equal to 0, and d2y by dx squared equal to 0 is a point of inflection. So therefore, we know that this is the point of inflection, and we know that x equals 3 was a local minimum. As you may have gathered, this is a section B question. So find the coordinates. Did we find the coordinates? Yes, we did. Of the stationary point, yes, we did. And we determined their nature, yes, we did. So now what we're working at is we're looking at the x and y intercepts. So we're now looking at the x and y intercept. So we do some different colours so it stands out. So we've got x intercept means where does it cut the x-axis, and we know it cuts the x-axis when y is equal to 0, and we know that y is equal to x to the power of 4 minus 4x cubed. So we're looking at x to the power of 4 minus 4x cubed is equal to 0. So we're taking x out as a common factor, and when we take x out as, or x cubed out as a common factor, we've got x cubed on, and it's going to be x minus 4, or to be, equal to 0. And what we have here is we've got a triple solution, which is, so we've got x equals 0, and we've also got x is equal to 4. Now, from last year's work, we've actually got x equals 0, x equals 0, x equals 0 3 times. And we know that when it's x equals 0, x equals 0, x equals 0 3 times, that we know that we have a skip. And of course, a skip is actually a point of inflection. So we're now looking at, so that's the end of that one. We're now looking at the y-intercept. Which is, the y-intercept is when x is equal to 0. So we've got y is equal to x to the power of 4 minus 4x cubed. So we've got x is equal to 0. So we've got 0 to the power of 4 minus 4 on 0 to the power of 4. So therefore we've got y is equal to 0. So we have this intercept is going to be x equals 0 and y equals 0. I forgot to write down the coordinates for these ones. So when x equals 0, y equals 0. so there was no need to do this. Whoops. And we've also got when x equals 4, y is equal to 0. All right then. So now we're in a position to sketch the graph. It's a power of 4. It's a positive power of 4. So before we sketch the graph, let's just write down what we have here. We've got y is equal to x to the power of 4 minus 4x cubed. It's a positive power of 4, so it's going to start up there. It's got a point of inflection at 0, 0, and it has a local maximum at sorry, I made a mistake. Oh, shocking. Absolutely shocking. When you input, I made a mistake here. When you input 3 into this, it's not plus 27, it's minus 27. Sorry, I've just realised my error. My apologies. Hopefully you've already picked up on that. So the input number is 3 and the output number is minus 27, and that's going to be a local minimum. So we've got a local minimum at 3 minus 27, and we have a point of inflection at 0. And let's now try and draw this. So I think I need to go to a new page. It's getting just a little bit cluttered, so bear with me. So going to a new page, let's quickly summarize what we've got so far. What we've got so far is we've got y is equal to x to the power of 4 minus 4x cubed. We've got a point of inflection at 0, 0. So there's a point of inflection. Sorry about the mistake earlier on. Or did I make a mistake? No. So we've also got a minimum at 3 minus 27, which is a local minimum. And we've also got it cutting the x-axis at the point 4, 0. So that's where it cuts the x-axis. It's a positive x to the power 4. So therefore, when we come to draw this, we know it's starting up there. So using all this information, we are now going to put this problem together. So knowing all this information, we're going to put this problem together. Also, the range of values that the domain of values that we're allowed to use is -1 is less than or equal to x is less than or equal to 4. So go back and check that. Yes, that's the very last bit. When we come to sketch this function, I didn't highlight that earlier on, we are using that domain of definition, so that's quite important. Right then, sketch is, you still have to do it neatly. So when you're doing a sketch, you still have to draw neat axes. If you don't, you will lose marks. So I just want to put that on the line to make it look a bit nicer. You should label the axes, otherwise you will lose marks. And then you should put in the key points. The key points is that we have a point at 0, 0, which is going to be a point of inflection. We're going to have a point at 1, 2, 3, and we're going to have a point at 3, and that is a local minimum. So we're going to do -9, -18, -27. This is a sketch, so it doesn't have to be perfect. So we've got another point here, and that point is a local minimum. And this is the point 3. So there's another point which we now have to calculate, because we're allowed to use up to x equals 4. And we've also got to calculate a value for x equals -1, which is going to be here. So we have to calculate those 2 points. And that only became apparent as I was sketching it. So now I'm back to here, where I've got y is equal to x to the power of 4 minus 4x cubed, and I've got an input number of x equals -1, where y is equal to empty bracket to the power of 4 minus 4 on empty bracket to the power of 3. I've also got x is equal to an input number of 4, so y is equal to empty bracket power of 4 minus 4 on empty bracket to the power of 3, and I want to work out the 2 output numbers for these 2 input numbers. Now, the output number for -1, again, you can reach the calculator or you can do it in your head, is going to be 5. And the output number for x equals 4 is, we've actually already done it, is actually equal to 0. Okay, so now we already knew from up here that when x equals 4, that y was equal to 0. We know that this point here is a minimum, so I can draw it up to there, and we know that -1 has an output value of 5, so that was 9 going by the thing here, but this is a sketch, it doesn't have to be perfect, so I know that 5 is roughly there, but I could have done it slightly higher. We know that this thing here is a point of inflection, so let's do it in a slightly different colour so that you can see it. This is a point of inflection. The point of inflection is where the graph goes flat. So because that's a point of inflection, I can now go down to the minimum, and because it's a point of inflection, I can now go flat and then go up. So point of inflection is also a place where it skips. Now that was ever so slightly untidy, so quite like the idea of doing that again. So it comes out to there, and that's the point -1, 5. Now, have we answered all the questions? Well, let's just go back and just check. The very last question is, what is the maximum value of y on this graph? What's the maximum value of y on this graph. Now this is interesting because the maximum value of y on this graph is in actual fact the point here, which is not a local maximum, but it is the maximum value. Now the maximum point, let's finish it off here. This is for the very last part. So the maximum point on this graph is in actual fact for, -1, (5). But it didn't ask you for the maximum point, it asked you for the maximum value. And the maximum value is always a y equals value, and the maximum value is y is equal to 5. The maximum value is y is equal to 5. And now we've finished off that problem. Now what I need you to do is not to do a question from the book. I need you to be able to go through and be able to do that example without having to look it up. So your homework, if you want to aim for a H2 or a H1, is to get all of that right. Very important. Now, we're on to example 14.8, which is an example in the book. And this time the exercise questions up on the right-hand side are from the textbook, not from the worksheet. And what you have here is you've got the graph. I think I might have copied this down right. The graph of a cubic function is shown in the diagram. So here, need to rewrite that. The graph of a cubic function is shown as in the diagram. Now, when you differentiate a cubic function, let's have a look down here. When you differentiate a cubic function, so you've got y is equal to, let's just write down a general cubic function, ax cubed, just a basic simple one. When you differentiate a cubic function, dy dx, you are going to get 3ax squared. You are going to get a quadratic function. So when you differentiate a cubic, you will get a quadratic. So that's just there to help you focus. So when you differentiate a cubic, you will get a quadratic function. All right then, one of the 4 diagrams below shows the graph of the differential of the above function. State which one it is and justify your answer. Okay, so the way we do this is we go back to the cubic and we look at we go back to the cubic and we are actually going to be looking at the slope. Now, and the slope, what they're saying to you is A, B, C, D are all quadratics, but only one of these quadratics will match the one above. Now the problem is they've labelled the axis y, but these are meant to be differentials. So the y-axis should have been labelled dy dx because they are meant to represent the derivative of the function above. So just highlight that. The y-axis should be labelled dy dx because they're meant to represent the derivative of the above. So the very next thing we've got to do is we've got to relabel all these y-axes. And you need to do that in the exam as well because they'll deliberately put y's in just to throw you off. So now we know that these graphs are meant to be representing slope functions. We're now going to look at the slope on this quadratic. So what I'm doing here is, if I start at the very first section of this graph, what do I know about the very first section of this graph from the very first video? It's an increasing function. So the very first part of this graph, the dy by dx value is going to be a 0. The dy by dx value of the very first part of this graph is going to be a 0. So the very first part of that graph, the dy by dx, all the way up to the first section, is going to be 0. At the very top, when it tops out, what's it going to be? What's dy by dx going to be? Come on, you should be able to tell me. Well, where it tops out at the maximum, the slope is going to be 0. So we now know that the slope at the very top is going to be 0. So in the first section, the slope was, sorry, do that again. The very first section, the slope is a plus. When it gets to the top of the first section, the slope becomes 0. Okay. As we go to the next section, as we go from the 0 all the way down to here, what do we know about this section of the graph? It's a decreasing section. And if it's a decreasing section, we know that the slope is minus. So on the next section of the graph, we know that the slope has to be a minus. And when we get to once we get to the bottom of that section here, we know that the slope here is going to be 0. So on that section, the slope, the very bottom, the minimum slope is 0. And then what happens is on the last section of the curve, this curve is going up. Because it's an increasing part of the curve, we know for this part, the slope will be positive. Okay, so what we're going to do now is we're going to look at these 4 pictures. And when we look at these 4 pictures, we're looking at the value of dy dx as we travel along the blue line. So if we travel along this blue line, to find the y values, all we ever do is we draw a horizontal line across. And as we're noting from here, oh look, for this graph, the y values, no matter how high I go, are always negative. It never gets above the x-axis. So for this graph, dy dx always remains negative. So therefore, this can't be the graph for the dy dx. When we look at this graph, let's just pick an arbitrary point. Let's pick this point here. What dy dx value does it give? It gives a positive value. What does it give here? Positive value. What does it give here? Oh, positive value. So this graph only ever gives positive values. Now we're going on to C. So what do we know about for this section of the dy by dx? It gives a negative value. What about this section? Still gives a negative value. What about this? This section is on the 0 line, so it gives a 0. Already, it doesn't match what I'm doing here, so I can reject it. So that doesn't work. Now I'm on to the D1. So the first x value, if I draw it going across, what does it give me? It gives me positive values. Right. It gives me positive values all the way down here until I get to here. What does it give me here? When I travel across, it gives me a 0. Right, so the first 2 are working. And then if I go onto this section of the graph, what does it give me? Negative values. And it gives me negative values all the way round. Always negative values, a negative value. Until I get to here. And because it's on the x-axis, it gives me a 0. So I've got a positive, negative, and 0. Now onto this section of the curve. And what dy dx value does it give me here? It gives me positive ones. So now it matches that one. So D is the answer, and that's the justification for it. So the answer is D. By the way, I moved the pictures around. It's not identical to the example in the textbook because D was at the front and you get the answer too quickly without the reasoning. So that's the way I do it. It's fairly simple. You need to be doing question number 17 and number 18. And that, I think, is the end of the video. Now what you've got here is there was some worksheets that I wanted you to do. And the worksheet was 11b. So this is the first part of 11b. So you need to screenshot this and work off it. And then you've got the rest of 11b, the rest of the questions. Again, you need to screenshot it. And then, of course, you will want the answers, and the answers are here. So you need to screenshot this page as well.